So I'm getting a little bit of pushback on the loops. How in the heck are you tuning these loops? How do you know that you've got the loops matched? What are you doing with these coupling loops and matching methods? I don't see any instruments. And I can say that with receiving loops, which are not the same thing as transmitting loops, you can do a lot with just your ordinary radio receiver and listening for signals and peaking the signals. You don't need to have a $130,000 Keysight PNA-X 4-port VNA to be able to do this job. In fact, you don't even need a nano VNA. You can do it with very simple instruments. And here at Microwave One, we try to keep it really simple. You've got your SWR meter and maybe a little QRP rig. That's one way to do it, to match the SWR with these loops. Maybe you've sprung for some type of MFJ antenna analyzer. This is a very early one, very primitive. It only goes down to 1.4 megahertz, however, and it's pretty low power. You might have a problem exciting the loop with something that's this low power. So of course it turned into a project which I did not anticipate. I was doing a loop down at a low end of the broadcast band and down to 470 kilohertz for the 630 meter band. I didn't have anything. So I ended up building a little oscillator. This is background stuff. I built this little oscillator and it goes from 400 kilohertz to 1 megahertz. Okay, it's kind of a W7ZOI design, except I used a bipolar transistor as the emitter follower buffer instead of a FET. And it has, one of those patented wideband output transistors. I think this is a 2N 3053. Radio Shack used to sell those. This thing puts out 50 milliwatts at least, probably closer to 100 milliwatts of RF, and that does light up the loop nice. But then you have to measure it, and again you have a problem because your SWR bridge doesn't work that low. You've noticed how they get very insensitive at low frequencies. Really at 80 meters you have to almost turn them up full when you're using QRP. So I had to build an SWR bridge as well, and here's a little homemade SWR bridge using the standard 4 resistor method, bridge method, and this works out really slick. So now I can measure the loop all the way down to 400 kilohertz using this simple setup. So you guys are probably going loopy by now with all of this loop talk. This is the 1949 ARRL antenna book, and loops are touched on even back in the early antenna manuals. But the small loop is looked at as kind of an anomaly and is only given a very small part of the write-up, and they talk about it as being useful at lower frequencies for radio direction finding, that kind of thing. So clearly the QRN, the interference and the man-made noise problem is not as big of a deal back then. And now we're using the loops for a new application, that is as a small transmitting loop. So we're seeing more and more interest in loop antennas compared to in the old days. So in this last video on the large loop, we finally tune a coaxial loop, and we use a coaxial pickup coil. So I'll be using a combination of a tuning capacitor along with a multi-capacitances on it to hit each band. And of course we know that our loop is only really effective from 75 meters down to the low frequencies because of its size. It's not really effective as a tuned loop unless it's a wire loop. With coax we're going to find that there's a lot of capacitance in the coax. That's going to restrict our upper end. But certainly the loop is most useful from 75 meters, 160 meters, the 630 meter band, and the newer low frequency band that's available to hams. That's where these loops are really going to come into their own, and they're going to help you to hear those signals, even with your SDRs. So you might remember on our Untuned loop that we're basically taking a fairly low impedance from the loop and transforming it up to the impedance of the coax. Now once we attempt to resonate this loop, and remember we have the split at the top, and let's say we put a variable capacitor at this point to resonate the loop, that is going to produce a high impedance because it's a tuned circuit. It's a parallel tuned circuit. You can think of the loop as just an inductance. So you need to transform a fairly high impedance down to the low impedance of the coax, just the opposite of what we're doing with the untuned coax loop. Okay, so this thing is only covering from about 2 megahertz to 4.2, so it covers the 80 meter band and down to 2 megahertz, but it's really restricted the band. Has to do with the capacitance that's in the coax. That static capacitance is affecting the amount of spread we can get with the loop. Obviously doing a good job with W1EW code practice around 5 o'clock. So as you see it, this particular setup with the single loop of coax and the coax pickup is not going to be able to handle 80 and 160 unless maybe we used a 4-gang capacitor. But you certainly could do it with fixed capacitors and have this probably operate 80 and 160 and possibly something in the middle of the broadcast band. So I've made a bit of an error on my calculations. The pickup loop, which I wanted to be between 1/5 and 1/4 of the size of the other loop, is incorrect. It's 1/5 of the diameter of the loop is what you want the pickup loop to be. So I'm now going to reduce the size of this. Looks like it's almost 4 foot, that loop, that pickup loop, down to about 20 inches. So we'll see if that makes a difference. So I've been trying some various fixed capacitors on here to see how low in frequency we can get this thing to go. These are your typical silver micas, high Q capacitors, and running into some interesting effects. This thing is not behaving as well as I'd like it to do at the broadcast band frequencies. I don't think there's enough inductance here, and with the added capacitance of the coax itself, my tuning ranges are very limited. So let's do some calculations and find out what's going on with this loop. We have this big coax loop now. It's a single turn, a single 27-foot circumference loop, and it's working out to have an inductance of around 5.8 microhenries. Our 3 times 365 picofarad tuning capacitor is a total of 1095 picofarads. So using the resonance calculator, this comes out to around 2 megahertz. Sure enough, we're resonating just below 2 megahertz, around 1.9. Why just below? Well, we have effective capacitance represented by some portion of the RG6 coax. It's approximately 220 picofarads per 100 feet. So there's some portion of that that we're seeing. Also, the minimum capacitance of the gain capacitor, there's some static minimal capacitance there. There's some strays. Certainly there's some effects by the 2 loops together. So we end up with a shortened tuning range of 2 to about 4.7 megahertz. which gives us 80 meters, but we don't quite get down to 160. But by adding about 100 or 150 picofarads of capacitance, a static capacitance we add, or a padding capacitor, we do get to 160, and we do reach 80 meters at the top. So you can still do 160 and 80 with one sweep of the dial with our single loop of coax. How about the broadcast band? Well, if we figure we have around 1,300 picofarads of capacitance at full mesh, if we add a 470 puff cap, that drops us to about 1.6 megs. That's the top of the band. And a 1,000 puff capacitor, that takes us down to about 1.4. We're not getting anywhere. The point is, we're going to need a lot of C to get down to where we need to go in the broadcast band. So the single turn coax loop is not working out too well. And the 3-gang capacitor is not effective at giving us a full tuning range on the broadcast band, that's for sure. So, I think we're into the idea of the multi-turn wireframe loop again. You need a little more inductance. If you really want to tune the whole broadcast band with a single 365 picofarad variable, you're going to need a frame type loop, a small one with a lot of turns. And they're going to have to be spaced so you don't have a lot of capacitance between the turns. So, lesson learned, 3 turns actually takes you a little bit too far. You can't tune much higher than 1 megahertz or 1,000 kilohertz with 3 turns. So 2 turns looks like the sweet spot for the broadcast band. 1 turn for 160 and 80 meters, 2 turns for the broadcast band, and the 3 turns that I've managed to put on here, we're going to see how that acts at the lower part of the broadcast band and in the 630 meter band. Okay, I wanted you guys to see it. I didn't think you'd believe it unless you saw it. I've got 3 turns of 75 ohm coax on this loop. Or some people call it the 600 meter band. We have a very small band segment between 472 and 479 kilohertz. So really you could do that with a fixed capacitor, but I thought I would try it with a variable capacitor solution. So for the 630 meter idea, we're definitely going to need more inductance on the loop. And it's going to start to look silly because I'm going to put 3 turns of coax on that same frame. And it's going to get a little bit heavy, a little bit hard to handle, but I think it will fit on there. You guys might remember that there are 2 square terms in the old solenoid coil inductance formula, and both of them are on the numerator up top. So basically, if you double the number of turns or double the diameter of the loop, you increase the inductance 4 times. So going from 1 turn to 2 turn, it's 2 squared. So if we have around 6 microhenries for 1 turn, 2 turns would give us 36 microhenries. And an added turn, or 3 turns, will get us up towards 60 microhenries. Now remember that old rule of thumb we have, that we make the diameter of the coupling loop 1/5 of the diameter of the major primary loop? Well, what happens when you start to add turns to your primary loop? What happens if you have a 3-turn primary loop? What are you supposed to do with that coupling loop? Okay, so I'm at 368 kilohertz, and with a couple of 820 puff caps across the variable, I'm able to resonate the 3 turns quite nicely. I am noticing as I go lower in frequency by adding capacitance I'm starting to lose some sensitivity. I think that's because the pickup loop is starting to look too small. So this is where we need the larger pickup loop in the middle in order to get back some of that sensitivity. That guy's just a little bit too small. We need to increase that again. So let's try to null it out. Of course, at this frequency, the loop looks much smaller, and we get almost a perfect null. This is really working well. So I think the 3 turns is excellent for the low frequency band. It's just we need to increase the size of the pickup loop. I think you'd have a pretty good situation with a tuned all coax type solution. So for 600 meters, or what we call 630 meters, I think the 3 turns works very well with just a regular 4-section variable, or perhaps a 3-section with an 820, or a 2-section maybe with a 1500 puff across it. Single 24-inch loop that's located towards the top, and I'll show you that. Now this is a coaxial loop, a shorted coax loop, and it's really doing quite well. So I think what I'm going to do next is build a triple coaxial loop in that position, and we'll see if we increase it from the 70. Okay, so we're actually above the mark now. We have a proper coaxial triple loop up on the antenna. As you can see, the output is even higher now that we have everything set up. So I'll show you what it looks like up top. Okay, we're going up. Take a peek and see what that triple loop looks like. A little bit tough to see. Let me take the camera off. Okay, so you can see that the triple coax loop in the 100% coax big loop is up there. Our signal strength has gone up. No doubt our match has improved. Now you might notice I haven't been using any form of match it, tuner, SWR bridge, analyzer, VNA, nothing like that. We're just using the receiver and a little bit of math to come up with something that works. But I just wanted to show you that the triple coupling loop goes right along with the triple primary loop. So I found with my SWR bridge that I'm getting a better match when I do, you know, the proscribed thing, which is to, you know, put the pickup loop very close to the outside of the main loop. And I also reduced the number of turns from 3 to 2, and that also improved the SWR. So my original theory about matching the number of turns doesn't hold completely. You still have to tune the coupling loop if you're going for a transmit type situation. But truthfully, I'm not noticing much difference. Once you get the SWR down to about 3 to 1, you really can't tell anything on the receive end. Now, of course, I'm using a short piece of coax. Maybe across the lawn or something, you'd start to see some of that come into play. But certainly with low-loss coax, it doesn't have to be perfectly matched like a transmitting loop has to be. Okay, here's a New York station, 880. Let's see if we can get a null on it. Nice. Not bad, not bad at all. The most effective type of inductive coupling loop is the shielded or screened loop, often referred to as a Faraday loop. As with the unshielded coupling loop, the typical diameter is 1/5 that of the main loop, though some people have better results with the coupling loops a little larger or a little smaller than this size. There are a number of variations in coax coupling loop styles. Whether the coax is interrupted at a point halfway around the loop, or whether the center conductor is interrupted at that same point, how the braid and center conductor are connected at the starting point of the loop, there's all kinds of different variations. The coaxial coupling loop design in my early testing was a simple open shield with the center to the shield of the feedline type. That's the wraparound and put the center of the coax right to the shield. For ease of construction, the coupling loop is typically made of a section of coax cable. Hey, you said it was 1/5 of the diameter. I've heard other folks say it's 1/5 of the circumference. Who's right? Well, it turns out they both are. Work out the 9th grade math for fun, and you'll see that they're equivalent. This type, while easy to build, is not the best coupling loop type because it's inherently unbalanced, making it susceptible to the dreaded vertical E polarization noise sources we're trying to avoid. Instead, the half-shielded loop style produces equal and opposite polarity in the vertical sections that cancel out the vertical energy, making the loop primarily sensitive to horizontal energy. Unfortunately, it's not really a Faraday shielded loop anymore, but with this top feed method, the left-hand and right-hand halves of the coupling loop generate opposite canceling voltages. They're canceling in the vertical direction, so the average becomes close to zero. This eliminates receiving and generation of vertically polarized E fields, but you still get reception of horizontally polarized E fields. So it's probably worth mentioning some more avant-garde feed methods for the tuned coax loop antenna. One that's gaining popularity is a single-turn toroid feed. This style is sometimes accused of questionable efficiency for transmitting loops, but it's a natural for a receiving loop. The next is any number of capacitor-coupled arrangements, including this excellent approach by G3 X-Ray Golf Charlie. What about measuring SWR on your receiving loop? Well, generally, most people just tune for maximum noise in the receiver or maximum signal in the receiver. It's actually easier to tune on a live signal or signal-generated signal than it is noise, but you can very easily tell where the loop is resonant. And theoretically, it should always be possible to have perfect coincidence between the peak reception and SWR minimum. However, in the real world, coupling into the loop for maximum efficiency, as with a transmitting loop, drives some considerations for coupling that can skew the two. With a receiving loop where balance and noise rejection are the paramount goals, loss and lower Q can be more tolerated. So with many practical transmitting loop feed styles, the point of lowest SWR will not always exactly coincide with the point of maximum reception. So I hope all of you have enjoyed this series on the larger loop antenna. It might be a little much to put in your yard. You're probably going to think about Armstrong method for rotating it. Maybe some of you guys are going to put a motorized capacitor on it. But I like the coaxial untuned loop. Of all the types we've tried, I like the put it out there and forget about it nature of not having to flick a switch, worry about tuning. The untuned coaxial loop, that's my vote for simplicity and bang for the buck.